Regarding the actual energy in the spring, as mentioned previously, that is known as elastic potential energy. Elastic because the spring wants to snap back to its original shape, as all elastic objects do. Potential because it's stored in the spring. Until I release that energy, it's not going to result in any work being performed, any motion, etc. So, in order to understand where elastic potential energy, the equation comes from, I just want to jump right back to the data we collected during our Hooke's Law lab, or the data that Hooke himself calculated or derived. And if we look at a force displacement graph, in the previous video and in the previous concepts regarding Hooke's law, we looked at the slope of the line and discussed how that gave us information regarding the stiffness or the K value of the spring. If you remember back to the first marking period when we discussed graphing motion, there were two things that we looked at. The slope generally gives us information regarding whatever we're studying, and the area is another component that will give us some information as well. So if we decide to calculate the area underneath this curve, the area between the x-axis and my line, we find that we get, in this case, a triangle. A triangle that has one side that is force, measures force, and the other side that measures the displacement of the spring. So the force acting on the spring and the displacement acting on the spring can be utilized to calculate this area. Well, we know the area of a triangle is 1/2 times base times height. Now in this case, the base is the displacement and the height is a measurement of force. So if I replace the base with displacement and the height with force, we wind up with an equation that says 1/2 times the displacement times the force. We realize Hooke's law tells us that the force is also equal to k delta x. I should be able to replace F with k delta x, and when that is done, I wind up with 1/2 delta x times k delta x, which simplifies to 1/2 k delta x squared. Now that was a fairly lengthy derivation in terms of some of the things we've looked at, but the important takeaway is to kind of understand where this equation comes from, and that 1/2 times that spring constant times the square of the displacement of the spring will give you the elastic potential energy stored in that spring measured in joules, as is all energy. So this is the equation we're going to need to utilize moving forward. You won't necessarily have to be able to derive the entire thing from the graph, but it's a good idea to understand where these equations come from. And now, how could that equation be used to give us some information? Well, if we look at this example, if we're given a spring whose K value is 150 newtons per meter, and that spring is compressed 8 centimeters, how much elastic potential energy is now stored in the spring? How much energy do I now have that I can use to perform work or launch an object, something like that? We should first, as always, get our variables in order. We know the displacement that the spring experienced was 8 centimeters, but we hate centimeters. So if I convert that to 0.08 meters, we should be good to go. We're also given the K value, which is 150 newtons per meter, a little bit stronger than what we've dealt with before, still not by any means the strongest spring that you would experience. But if I know my K value and I know my displacement, I can always calculate not only the force due to Hooke's law, but now we can also calculate the elastic potential energy in accordance with this equation. So we know that the elastic potential energy is 1/2 k delta x squared. So if I plug in my k and I plug in my displacement, I will find that 0.48 joules of energy is now stored in this spring. Whoever pushed this down performed that much work on the spring, and that energy is now stored in an elastic potential form. It's a fairly straightforward equation. It's important to realize once you have the K value and the displacement, you can essentially analyze virtually anything about the spring, the force that it's exerting on the object, the elastic potential energy inside. A lot of information you can get from just those two values. More importantly, would be utilizing this concept of elastic potential in energy conservation. If you think back to when we first started the conservation of energy, we discussed the fact that the potential plus the kinetic plus the elastic potential before must always equal the gravitational potential plus the kinetic energy plus the elastic potential afterwards. Now, in previous examples, this always went away to zero because we weren't considering the presence of springs. The good news is the concept is no different than what we analyzed previously. We just now have to realize that since we have an equation, we are now capable of calculating energy transfers when a spring is involved. And just to show you a quick example, I have a ball that has a mass of 5 kilograms, traveling with a velocity of 4 meters per second, and is about to slam into this spring that has a K value of 100 newtons per meter. We're going to ignore friction in this case, as we usually do, and answer the question, how far will this spring compress? Now again, using the same concepts from earlier in the marking period, we can realize that all the energies before, kinetic, gravitational, and elastic, must equal all the energies afterwards, kinetic, gravitational, and elastic. Now, before, I have no gravitational because I have no height, and I have no elastic because I'm not compressing a spring. I do have velocity, so I obviously have kinetic. Afterwards, when this spring has been fully compressed, that means the ball is no longer moving. That spring has slowed it down to the point where the velocity is zero, and this spring has reached maximum compression. No kinetic because my velocity is gone, no gravitational, I still have no height, but I've now compressed the spring, so I do have some elastic potential energy. So if I eliminate the values that are zero, I essentially come to the realization that all the kinetic energy I had before must become elastic potential energy afterwards. I can then use my 1/2 mv squared equation for kinetic energy and my newly acquired 1/2 k delta x squared for my elastic potential energy. And when I plug in the values I was provided up top, I will find that 0.80 must equal delta x squared. You obtain 0.8 by multiplying this and then dividing by 50 because that's half of 100. And if I take the square root of both sides, you will find that this spring will compress 0.89 meters. All the kinetic energy the ball had was transferred and became elastic potential energy once the spring was compressed. Another example, no different, seems like a little bit more complicated, would be if I had a 15 kilogram ball that was at rest on top of a hill, and there was a spring whose spring constant was 200 newtons per meter. It has been compressed 5 centimeters, and the initial velocity of everything up top is zero. So much like you would kind of put like a dart in a dart gun or something like that, this spring has been compressed, a ball has been placed in front of it, and you're about to launch this ball by releasing the energy in this spring. If you're at the top of a 20-meter hill, the question becomes, after this is launched and travels down the hill, how fast, what will its velocity be at point B, at the very bottom of this hill? Similar to what we did previously, all the energies before must equal all the energies afterward. I have no velocity up top, so the kinetic goes away. I do have height, so I have gravitational, and I do have a compressed spring, so I have some elastic potential energy. Afterwards, at the bottom, it's certainly still moving. There's no height, so there's no gravitational, and the spring is no longer compressed, so there's no elastic potential energy. I should then realize that the gravitational potential energy and the elastic potential energy up here at the top, due to the height and the compressed spring, will all be converted into kinetic energy at the very bottom. I can then use my MGH equation to calculate gravitational potential, my 1/2 k delta x squared equation to calculate my elastic potential energy, and my 1/2 mv squared equation to calculate my kinetic energy. You can see here that two of these energies are known, one is not known, but I can solve for it in terms of velocity. And if I solve this out, you'll find that about 2,943.25 joules must equal 1/2 times 15v squared. And if you solve all that out, you should find that your velocity at the bottom is about 19.81 meters per second. So the important thing to realize from all of these and these examples are that the process is no different. It's not really a new concept in any way. We're taking an old concept in which we ignored the elastic potential energy and just adding that one additional step. But outside of that, the process is entirely the same. So if you didn't have trouble with that before, just take a step back and realize it's no different. You just now have another equation that you'll likely have to include in any problems that have springs.